Good morning or afternoon, everyone. Welcome to the NAI Director Seminar. This is going to be the last Director Seminar before the summer break, and we'll pick it up again at the end of September. We are really privileged today to have David Blake of the NAI Ames team with us. Dave, as I'm sure most of the people listening to this and watching this know, is the principal investigator on the CheMin instrument, which is going to fly to Mars on the Mars Science Laboratory. And I was just looking at Dave's background, and I think he has probably been a principal investigator in just about every RNA program addressing planetary science and astrobiology that NASA has ever had. He's been a PI in the exobiology program, cosmochemistry, ancient Mars meteorite program, ASTID, Mars instrument development program, upper atmosphere research program. The list just goes on and on. So Dave has had quite a successful career here at NASA. He has in fact been here at NASA Ames, since he became an NRC fellow in 1986, and has had a very distinguished career, including presently being chief of the exobiology branch here at the center. He has a bachelor's in biological sciences from Stanford and a master's in geological sciences from Michigan and a PhD in mineralogy from Michigan. So Dave again represents the kind of interdisciplinarity within a single individual that we think we've invented here at NAI, but obviously it was invented long before us by people like Dave. So without further ado, I'll turn it over to Dave Blake.
Thanks. Actually, I think it was invented here because my advisor, when I graduated, the best thing he could say about me was that I was neither fish nor fowl. Mm-hmm. So whatever that means, hopefully something good. Well, I wanted to talk a bit today about the CheMin instrument and MSL, and one of the reasons for that is I know that NASA wants all of us scientists to get more involved with missions, and I know the NAI here at Ames is trying to do that by getting involved with CheMin and with MSL, and I wanted to offer that opportunity to anyone who wanted to do that. So let me begin by speaking a bit about MSL and what it is. It's going to mostly be boilerplate because I hope that you know about that already, and then I'll get into the CheMin instrument and how this might be useful for what you folks are doing. So okay, let's start off. Well, NASA's exploration program, this is also pretty much boilerplate. Presently, Phoenix is on the ground and getting some pretty good data. And October 2009 is the launch of Mars Science Laboratory, and it'll land in mid-2010 and be active on the surface hopefully for at least 2 years. And then what happens after that, no one knows. Depending upon what discoveries we make and what NASA policy is at that time. Well, MSL and CheMin science goals. The MSL science objective is to explore and quantitatively assess a local region on the Mars surface as a potential habitat for past or present life. And there are 4 main science objectives: assess the biological potential of a one target environment, characterize the geology and geochemistry of the landed region, investigate processes of relevance to past habitability, and characterize surface radiation. CheMin is going to be involved in 3 of those goals. The starred ones here: assess the biological potential, characterize geology, investigate processes relevant to past habitability. So just to show you what MSL looks like in comparison to MUR, it's a lot bigger. This is MSL in the front, and the main difference aside from size you can see is MSL is operated with a radiothermal generator, so it's nuclear powered. MSL is run, or rather MERs are run by solar. Here's a size comparison. I don't know if anybody really understands just how big this thing is, but it just about dwarfs a Mini Cooper. And I've never seen this close up, but I've seen some of the ones they use for testing the landing, and the top of this surface just about hits chest high on me, and these wheels are about half a meter in diameter, so it's big. They started out there. We're coming up on our third landing site workshop. The first landing site workshop, there were something like 30 or 40 individual sites proposed, and these were investigated by HiRISE and some of the other orbital assets on Mars. And they've been winnowed down to 6 with the potential 7th. And you can look on the web and see what's interesting about each of these sites. But they all have to do with either with water, with either phyllosilicates or with sulfates. Here's the MSL payload. There's 4 elements to it. There's a remote sensing element, which has a mass cam similar to what the MERS have. A ChemCam, which is a laser ionization tool where you can actually see compositions at a distance. Then there are contact instruments, including the MOLLE Ken-Edget's instrument, which is for microscopic imaging. It's like a geologist's hand lens. The APXS, which is flown on the MERS, and it will tell you elemental composition. And then inside the body of the rover, there are 2 analytical instruments. The SAM instrument, which is a GC mass spec from Paul Mahaffey at Goddard. And that's kind of like the 500-pound gorilla on the payload. Then CheMin is also inside there, and it's about a 10-kilogram XRD XRF instrument. And then arrayed around the outside of the lander or the rover, there's the MARTI instrument, which is strictly for descent imagery. There's the REMS instrument, which is a meteorology tool for determining wind speed and so forth. There's the RAD instrument, which tells you about radiation on the surface. And then there's the DAN instrument, which is a neutron generator and detector to determine subsurface hydrogen. And I was talking to Dmitry Mitrofanov, and the interesting thing about the DAN is that this really is swords to plowshares, because the neutron generator in that thing is a nuclear trigger from a Russian atomic bomb. So I thought that was pretty interesting. I'd like to see the U.S. pull that kind of a thing off on a Russian mission. Okay, let's get to CheMin. Well, I'm the PI, and it's being built by JPL, but it's coming out of NASA Research Center. There's a Microfocus X-ray tube that produces a small beam about 50 microns in diameter that goes through a pinhole collimator to illuminate the sample cell here, which consists of 2 thin plastic windows with fine-grained material in between. And then the photons are detected by this X-ray sensitive CCD. And I'll talk more about this later, but just to say now that CheMin is able to do definitive mineralogy and be able to determine all the minerals that are on Mars. And if we don't know, if we find a mineral that we didn't see before, we'll be able to name it and tell you what it is. Here's the most recent picture of the rover. The main things that have changed are things around the SASPA and the arm here. Nothing too much of interest. CheMin is sitting inside the rover, and there's a little access port right about here. When they generate material for us, they open a little access port, dump in the material, and then we analyze it. So here's the summary of spreadsheet of investigations versus objectives. These are all the objectives on this side of what MSL is supposed to do. And here's the various ways that the instruments support those objectives. So you can see there's a lot of redundancy in the package, and that's kind of like what they were going for. So now I'd like to go into the mineralogy aspect of this. Why do we care about mineralogy on Mars? Mineralogy is really the only means to elucidate environments in the geologically ancient past. Minerals are thermodynamic phases, and by that I mean that they form under certain conditions of temperature, pressure, and composition. And by seeing a mineral with it, you can tell what pressure, temperature, and composition surrounded it when it was formed. The second thing that helps us is that solid state transformations are sluggish. So minerals quite often stay in an unrequited state after they're formed, so we can see them and know what condition they were formed in, even though they're present now in a different condition. So if you happen to find a diamond on the ground, which would be a good thing, you could say that that diamond was not formed in that environment. It was formed in a high pressure environment somewhere else. Thirdly rather, relic biological information might be cryptic, and so you need to have mineralogy to find the rocks that may have relic bioinformation inside of them. So mineralogy is a good tool to find what rocks might contain biosignatures within them. And then lastly, weathering and diagenesis might only leave the mineral component of a biological process. The phrase I like to say is that anything older than a few million years on Mars is either going to be a rock or it's only going to be interpretable in terms of the rocks that contain it. So let's talk about mineralogy in the context of some rocks that were seen by the rovers. Here you see a table of a bunch of rocks from Gusev crater. These are what called Watchtower class rocks. There's Keystone, Keel Davis, Watchtower, Pequod, and Peros. And you can see from the APX data here, they're all pretty much the same chemically. So if you do APX of all of these rocks, they all pretty much look the same. But over here you see Mossbauer results, and each one of these colors represents a different iron mineral. And you can see that the mineralogy of these rocks, at least when looked at from a mineralogical perspective, from the iron minerals rather, are very diverse. So mineralogy will tell you the diverse environments of a surface, whereas chemical composition alone might not. So here's the CheMin principle. CheMin stands for chemistry and mineralogy. It uses X-ray diffraction for mineralogical determinations, X-ray fluorescence for elemental characterization, a single detector for both measurements, and no moving parts and about 20 milligrams sample size. So it's a little bit smaller than a baby aspirin tablet size of sample. So now I'll give you a little brief insight into how it works. Cobalt X-ray tube, microfocus tube. A beam starts here at about 50 microns diameter. There's a pinhole collimator which produces a collimated approximately 50 micron source. It goes through a two thin plastic films which contain the sample between them. The sample consists of 150 microns and below crushed powders, and this whole thing is shaken so that the powder flows like a liquid inside this cell, so that over a period of time all the grains pass through this tiny beam in random orientations. And as they pass through the beam, two possible things can happen. Nothing can happen, of course, but one possible thing is diffraction, and the diffracted beams form these Lowy rings on the CCD detector here. The second thing that can happen is that you can get X-ray fluorescence, and photons are emitted from the sample which have energies which tell you what elements are in the sample. And so this detector can collect both of those signals at once. If you do a 2 theta plot, which is basically from the center outwards of these photons that are striking the rings, then you will get this thing here, this one-dimensional plot, diffractogram, and this will tell you what spacings are present in all the minerals that are contained in the sample. If you just take all the energies of the photons that strike the chip and make a histogram down here, this will tell you all the elements that are present. So with these two measurements, you can tell the composition of the sample from the X-ray fluorescence and the structure of the sample from the diffraction information. So now that we know that, we know the geometry, it's a transmission geometry. Now we have to worry about the details of where do we want to look, what 2 theta angles, what range, what resolution. We know that we would like to see in the low 2 theta regions because we want to see clays, and that's where the principal peaks of clays are located. Here's XRD pattern of smectite, and you can see this is the principal peak of smectite, and that's located down around 5 or 6 degrees 2 theta. So we want to have an angular range that will encompass clays. We also want to go out far enough to encompass other minerals of interest. So this is a little bit of Monday morning quarterbacking. We actually knew where we wanted to go with this instrument, but when we went through the science peer review down at JPL to justify our 2 theta range, we took a mineral model of the Peace outcrop in the Columbia Hills done by Doug Ming, This shows you each one of the minerals that were present in that model. Forsterite, which is an olivine, augite, which is a pyroxene, labradorite, which is a feldspar, magnetite, chlorapatite, kieserite, gypsum, and this is all of them together. This shows the major peaks, all these small lines for each mineral. You can see there are very complex ones like the labradorite, which has a lot of lines together. Simple ones like magnetite, which is a cubic peak, or rather cubic phase. When you put them all together, you have kind of a mishmash here. And the main point we wanted to make with this is that if you look at the 2 theta range from about 5 out to about 50, you can get all the major peaks of interest for these phases. Okay, so let's go on to look at what kind of, we know the range of 2 theta we want. What kind of resolution do we want? And we can't just have the best resolution possible because resolution is inversely proportional to count rate. So we want to have basically the worst resolution that will give us the answer that we can live with. So what we did is we made a model of these minerals and used various resolutions here from 0.3. I know you can't see the colors here all together, but 0.3 to about 0.6 degrees 2 theta. And if we go to the next slide here, we'll just look at a small range from 30 to 32 degrees 2 theta. You can see that as we go from about 0.3 degrees 2 theta downward, we start to lose the ability to distinguish these peaks and therefore to distinguish these minerals. So whereas we would like to have the very best possible resolution on this instrument, we can put up with between about 0.3 and 0.35 and actually do the job. And just for comparison, a laboratory diffractometer that you might buy has a full width half max of about 0.1. So we're about 3 times worse than a laboratory diffractometer, but nevertheless we're able to do what we say we can do. And here's an example of a data set from a typical CheMin run. Here's the 2D energy filtered XRD pattern. And here is the diffractogram that was obtained from that pattern. This is what's called a Rietveld refinement, which is a full pattern fitting with Squyres refinement. And by doing this kind of a quantitative analysis, you can get a fully quantitative analysis of all the minerals that are present there. This was done by Dave Fish at Indiana University, who's one of the people on our team. You can also get, for anything more than about 10%, present about 10% composition, you can get refined lattice parameters. And with refined lattice parameters, with things like olivines, you can tell the iron-magnesium ratio and so forth. And then here's the X-ray fluorescence pattern from this sample. This particular camera had a bit of iron contamination. We won't really have that issue on MSL, but that's what a standard data set will look like. Now that we know what full range and all that is necessary, what kind of accuracy and precision do we want? This shows the accuracy of the ChemCam instrument and the APXS and the precision, and we picked an accuracy of about 15% of the amount present. We can actually do better than that, but this is our requirement. This is what we have to show in order to be fully responsive to our contract. And a 10% precision with a minimum detection limit of about 3%. And we can actually do better than this, but this is what we signed up for. Here's a couple of examples. This is a Hawaiian soil collected by Dick Morris. It shows the minerals present down here. This shows what our trial horse CheMin 4 instrument was able to obtain. This is a standard X-ray diffractometer analysis. This is the percentage difference between the two, and this is our evaluation. So basically, all of the phases that are above 3% are within 15%. This amorphous phase here we had a little difficulty with, and we knew all along we have difficulty with amorphous materials, and we're developing models for that. The rest of these are below the minimum detection limits, with the exception of kaolinite. And clays, we can't quite do what we say we can do. We're more like 10% with clays. Here's another example. This is a synthetic clay-bearing evaporite. And here again, there's non-ternite, gypsum, halite, hematite. That's what CheMin 4 data produced. That's the known mixture, and this is the deviation in percent. And these are all within our stated precision and accuracy of analysis. Okay, so I was interested to see what we could do with some amorphous materials, so I got together, I don't really think you can probably see the labels very well, but I got together as many amorphous silica materials as I could. This was to kind of look at similar materials to the amorphous silica that they saw at home plate in MER A. So the lines here you see, there's opal A, which is right there. Let's see, I believe that's opal A right there. Opal CT, fused silica in the red, and geyserite in the dark blue. Down here, here's fulgurite, which is a lightning strike amorphous quartz. It's when lightning strikes a sandstone. Then there's moldavite here. Moldavite is from Moldavia, Czechoslovakia. That's basically a tektite-like material caused by a meteorite impact. And then here's a tektite that I bought at the AGU. And then over here is a couple of asphalt tuffs from New Mexico. So basically the point I want to make, even without looking into the details, is every single one of these is different, and we can quantitatively analyze even amorphous materials and tell you what they are. Okay, so let's move on a bit here. Here's a little heritage of what we've done since 1991. This was our first instrument, built off a big Phillips tube tower. The weight of the instrument was 500 kilograms. That obviously wasn't going to go anywhere. In 2002, we got a bit better X-ray tube and power supply. We dropped weight a little bit to 100 kilograms. And 2004, when we started getting our major funding, we were able to make a field instrument which weighed about 30 kilograms. And we actually took this out to Death Valley and did some tests with it. From there, we moved on in two directions. This was used as a trial horse to build the Mars instrument, which is over here. It's actually being put together now and will be delivered by JPL in September. And it's pretty interesting to go down in the clean room and put a little your clean room garb on and see what they're up to. It's like having your own space shuttle built for you. It's just a lot of fun. Over here shows the second course we went with this. Philippe Saracen, who was my postdoc years ago, started a little company called In Situ in Mountain View, and he's still working with me. He's a co-I on CheMin, and he's building these what we're now calling TERRA instruments, which are commercially available, and they are instruments with the same geometry as the CheMin instrument, but can be taken in the field. They're field ruggedized and user-friendly. So let's go on. Here's our our trial horses. This is our CheMin 4 instrument, which we use to benchmark the MSL instrument. And then this is a bit more user-friendly instrument, our TERRA instrument, that we took out on the field for the first time in Spitsbergen last year. This one weighed about 30 kilograms, and Dave Bish and I carried her down off a mountain in Spitsbergen in 2006, and I about died. I knew that was not going to be the way we were going to go. So that was a major driving force for getting down to something a bit smaller, which is over here. This is still not easy to carry around. It's about 15 kilograms, but certainly a lot better than it used to be. So here's a comparison with what is available commercially. This is a portion of a Rogaku Miniflex instrument. And what you don't see in the picture is a 1 kilowatt generator and a water circulator that has to also be set up with it. And this is Ron Peterson, the discoverer of meridianite up in Canada in the wintertime. So we went up with him this year, and this is what he took, and this is the In Situ TERRA instrument. So this instrument is about 10 to 100 times smaller and all that other business than anything else that's available. Here's Dave Bish. This is the first time when we took CheMin 4 out to Death Valley to just do some cameo shots and do some demos. We didn't really take it out there with the idea of doing science. We really took it out there, I wouldn't say as a publicity stunt, but just to show we could do it, to show we could actually take an instrument in the field, and gather data. Spitsbergen, Svalbard, in 2006, we came out here to really do science. So here's Dave Bish on the top of Squyres with our CheMin 4 instrument. It's the first time anyone ever did a quantitative analysis in the field. And what we found is there are some really useful things you can do. You can actually actively generate hypotheses and test them in the field along with other people using other techniques. You can identify ephemeral phases that aren't going to last longer than a few minutes or a few hours, certainly not long enough to take them to the lab. And you can go through just a myriad of samples and find samples that you really want and not have to carry back the samples that you don't want. And this particularly is interesting for example, Doug Ming told me when he took our instrument down to Antarctica, sometimes they don't get their samples back for a year. So it's very good to make sure you know what you want and actually get some information on those samples when you're in the field. So here's next year. This is our CheMin, or rather our TERRA instrument. This instrument, actually, Philippe Saracen took this from a napkin drawing to carrying this on the airplane in 6 months. And it's the very same instrument I have today. This is on that same mountain up in Svalbard. If you don't know where it is, this is Spitsbergen. It's way north. This is the Arctic Circle here. This is way up at about 80 north, and the reason Bish had that gun in the previous slide is because you really do have to watch out for polar bears when you're up there. We were actually interrupted by polar bears a couple of times while we were doing work. Here's our first example of in Spitsbergen anyway, of why it's important to do mineralogy in the field. And I know you can't see the details of these two patterns, but you can see right here, you can see a couple of peaks here, and over here you see 3 peaks. Well, this is basically a calcite pattern. This was taken aboard ship a few hours after we collected the sample, and this one on the left was collected at Troll Hot Springs, or I guess you'd call it Warm Springs, and this line right here and a few others are indicative of monohydrocalcite. So we were able to find an ephemeral phase here that was not present even when we got in the boats and got back to the ships. Second thing we did up there, we had Steve Squyres along for 2 weeks of it, and we actually ran kind of a mock mission to Mars kind of a scenario where Steve Squyres and the Science Operations Working Group that we defined stayed aboard ship, and a party went ashore with the instruments. And what they did is they went to a place that we'd supposedly never seen, took images the way a rover would, took data the way the instruments would take data on MSL, and sent that data back to us. And then we were in this little enclosed room figuring out what to do next, where to go. And this shows you some of the data. This is CheMin data collected. We decided to go this rock. I personally thought it was a patch of snow, so we called it Snowy Rock. Turned out to be some kind of a granitic gneiss. And when we went there, we analyzed that, and so we knew what it was. That was pretty boring stuff. Paul Mahaffey decided to analyze. There were actually some lichens on here, so he tried out his SAM equivalent on the lichens. And this stuff's pretty boring to us, so we went and looked at the soil beneath the snowy rock, which shows a lot of amorphous material and some olivine and so forth. And then we moved on to a little outcrop that was not too far away from here, and this outcrop actually contained indications of some hydrous alteration. So it had some magnesite presence, so we were able to, aboard ship, go through the scenario of doing this with a rover and actually find a place of interest and go and sample there. So that's the story with that. That turned out to be a pretty successful campaign, and the next thing we heard, Doug Ming was going to Antarctica, so we didn't want to pass up the opportunity to send TERRA down there. So he went, I guess, with the Phoenix group down to Antarctica in January, and so here he is. Actually, this instrument worked in negative 20-degree weather, so it's pretty well ruggedized. He really didn't have any standing orders about what to do, so he had to figure it out for himself, but he's actually a pretty sharp guy, so he did a variety of things. One of the things he did he used mineralogy as an in-the-field guide to help out the biologists there look for nematode populations. And that's not probably the first thing you'd think of when you think of quantitative mineralogy, but by tracing the composition of the soil, he was actually able to point them in the direction of high nematode populations. The second thing that he did is he was able to map ancient glacial moraines using mineralogy. And the way he did this is that the more recent moraines had these sodium sulfate minerals, mirabolite and thenardite, and the more ancient ones had gypsum and calcite carbonate. So by just looking at the compositions of the phases, he could actually map the edges of these ancient glacial terrains down there. Philippe Saracen took TERRA up to British Columbia to the site location for the Meridianite discovery, and here it is. And basically this is a frozen lake, and these wooden areas, like right here, these big logs sticking out of here, would actually wick up this very salty water and evaporate it, and the crystals are found on this wood. And this is where Meridianite was found, which is a magnesium sulfate with 11 waters. It's a very hydrated magnesium sulfate, stable below 2 degrees centigrade. Well, turns out we didn't find any mirabolite. We didn't find any meridianite. It was too warm that year. But this was the composition of some salts we did find there. And lo and behold, when these were taken back to the lab and analyzed 2 weeks later, none of this stuff was there. So I think it's a big take-home message that the things you collect in the field may not be the things you analyze when you bring them back to the laboratory. A month later, I went to the University of Hawaii and I worked with Jeff Taylor. And I'm taking TERRA over to the Squyres Resolve campaign in November, so I wanted to work with Jeff on just do a little dry labbing and figure out what minerals and so forth were present. The first thing Jeff said is, well, why don't we try a real lunar sample? So he pulled out a lunar soil sample, and we analyzed it, sent it off to one of my co-Is, Steve Chipra, and he sent back a quantitative analysis, and it was just bang on to what Larry Taylor had analyzed by doing really difficult point counting techniques 10 years earlier. So Jeff was really excited by that, so we dropped the whole project of looking at the Squyres Resolve samples and did nothing but lunar samples all week. So this is a little graph of a number of samples from the moon that CheMin analyzed versus the same compositions by point counting. You can see we did a pretty good job, with the exception of a few examples here, of doing the very same quality of measurement as this meticulous point counting that literally took months and months of people's time on the Earth. And the CheMin instrument did this in a matter of a couple of hours for each analysis. I came back and I'd actually talked with Weifang Zhu, who's from the University of Wisconsin. I talked to him at the Astrobiology workshop here, rather the conference, and he asked if he could borrow this instrument to go on a field trip to Canada. So I said that would be fine. So when I came back, I flew up to Madison and dropped off the instrument, and I kind of felt like when I left my son off to his first day of school, I got back on the airplane, no instrument, no luggage, just got on the plane and left. And so Weifang and his students went off into Canada with this thing. And you can see they went to some very extreme environments. Here they were inside a truck stop bathroom in near Sudbury. They needed to recharge the instrument. That's why they went in there. But anyway, so they analyzed a whole bunch of samples. Weifang sent me this example of a quartz plus greenolite thing they got from one of the banded iron formations. And when they got back to the lab, they actually did some optical microscopy and some TEM, and this is actually the greenolite that was found in the XRD from the field. Just after that, Philippe Saracen took a different TERRA instrument, but over to Rio Tinto, Spain,
And we've been over there a couple of times, and Rio Tinto is an ancient mine that has a lot of iron sulfides, and these are oxidized to these very interesting iron sulfate hydrates, which we believe are on Mars, some examples of which are on Mars. And a lot of these things are also ephemeral, so what you look at there may not be in the lab, so we took a chance and went over there. This is Marc Galanou. Marc Galanou is a French scientist who actually did a theoretical diagram, theoretical model of the CheMin instrument, and actually came up with a ray tracing simulation so that we change any part of the instrument, and he'll tell us what it does at the output with counts and range and full with half max of 2 theta. So I was real happy to see Mark in the field. He's just been a mainstay for our program. Here's an example of a couple of things we found out there, or Philippe found rather. There's some hydronium jarosite that was, these are just on the rocks here from dehydrated salts. Here's an example of copiapite and cokimbite, also ephemeral mineral on the rocks there. Okay, so what's next? The reason I'm doing this is I'm interested in offering this to anyone in the NAI who cares to do this kind of a field campaign to do mineralogy, and the cost to anyone who wants to do it is just the process of sending it to you and getting it back, as long as you don't drop it from a great height. And I found the reason I can say this is we found for the last year that this is a fairly user-friendly instrument. It's very robust. It seems to produce information that is valuable from a wide variety of other disciplines. I've already got it signed up for the rest of this year to go various places, so it's going just about a different place every month. Starting next year, though, I'll have 2 of these things, and I'm willing to work with whoever wants to take this in the field. So just to conclude, and I hope I have time enough to do a little demo. I actually brought it. I'll show you how you prepare a sample and do an analysis. I think in situ mineralogical analysis is valuable for astrobiology field campaigns. Now it's quite possible for people who aren't mineralogists to do mineralogy in the field, and I'll show you how simple it can be. You don't have to be a mineralogist to do this. You should know a bit something. It's more than a toaster. And I think this real-time in situ mineralogy is a new concept, and I think we don't really know where it's going to go. Anytime you do something new, you don't know what all the applications are going to be. I had no idea we would be able to trace nematode populations in Antarctica. So you never know what you're going to find until you try it. So that's it, and I wanted to thank all my various funding. I'd hate to tell you how much money I spent on this, but it was just a ton. I'd like to thank NASA for providing me with all that money, and also to the CheMin team and to In Situ Incorporated, which is Philippe Saracen's startup company, which has made all this possible. So thanks.
Thank you, Dave. There is plenty of time to give a little demo. So what I suggest is, why don't you go ahead and get that set up, and if anybody has a question for Dave during the interim while he's getting set up, this would be a good time to jump in, and you'll have other opportunities to ask questions as we go along here.
And I can answer questions while I'm working. So here's the instrument. It weighs about 15 kilograms with batteries, and it's got 4 hours of life. It works off these laptop batteries, and these are hot swappable in the field. So you can just take a bunch of batteries and keep replacing them one at a time, or you can work for 4 hours and go home. So let me show you how to prepare a sample and load a sample. So it's perfectly safe. You're not going to be X-rayed by this any more than you'll be X-rayed by your color television set. The sample goes in here, so I'm going to start shaking the sample here. Okay, I'll show you what the sample consists of. It's basically a tuning fork arrangement And there are two symmetric sample holders, one on each side. So you fill one and not the other. And this is what we call the ashtray. So you put it in here, it shakes it just as if it were in the instrument. So what I'm going to do is I'm going to load a sample and then start it. And I'll show you how to prepare a sample. It's not always as easy as this. You don't always find a bit of your fireplace out in the field, but so that's what this is. This is a little bit of my fireplace. So this is a 150 micron mesh screen, and all I'm going to do is I'm going to take this little Dremel tool. Oh, thanks. And make some material. And I do this in the lab too. It's actually it's a very nice way to get a micro sample of something where you're interested in some horizon and not another horizon. So whatever goes through this screen will work with CheMin. And I don't know if you can see inside there, but there's a little bit of material in there. Not too much, but that's certainly enough to do the job. So what I'm going to do is I'm going to pour it in the sample holder here. This material needs to be fairly dry, so that there is an issue with using wet materials. They don't really flow into the cell very well. So that's one of the things we're working on. So I don't know if you can see that, but there are grains falling in there, and now they're being shaken around and filling this part right here. Okay, so that sample's ready to go. So now what I'm going to do is I'm just going to drop it right in here, and I'm going to stop shaking. Now from here on out, this can either be run by a computer or by any kind of web-capable device. If I have time, I'll show you. I can run it off my Mac iPhone. So this is going to be tough doing this left-handed backwards. Let's see. Okay, so this is the basic. There are only 4 commands on the instrument, so it's just dead easy to use. You can't make them. It has to be that way, or I would have messed it up. So this is the where you run everything from the status menu. Just click this arrow, say go, and you have to give it a name. And I'll say Blake's fireplace. Okay, and start. So you should hear it start going here pretty soon. Okay, so it's vibrating the sample, and the X-ray beam's on, and it's taking an analysis. And the status menu here tells you exactly what it's doing. This wouldn't be where you'd want to look all the time, but just to make sure things are going okay. To look at the data, you go to the data point here, the little data flag. And since this is actually talking to a computer that's running a web interface, so you're actually talking through the computer to another computer that's running the web. Okay, there's the first pattern. I have no idea if you can. Oh, you know what? I can hook that up here. I can now turn this to point it in my direction.
What's your web expert?
Oh,
Which
okay. Well, I'll just.
Oh yeah, yeah. We'll switch it to video.
Okay. Okay. Should I close this and open it to make it see the?
maybe.
Okay, so basically a pattern is it's developing. What this thing does is every 10 seconds it exposes the CCD. Oh, there we go. Okay, now I get to use my real laser pointer. So
Basically, now it's done 6 exposures so far. Every 10 seconds, it collects another analysis and sums it into the one you're seeing. Now, this does do X-ray fluorescence, and if you want to do X-ray fluorescence, you go to XRF. So this shows you the X-ray fluorescence pattern that's been generated, and what you see is there's the cobalt, K alpha, K beta from the tube. There's a little bit of iron in here. I don't know where the iron's coming from. There's calcium. Maybe I don't have it. Wow. Well, this is going dim, but you can see the calcium peak. So it gives you an idea. You might be seeing my fireplace, which is made out of calcite. Okay, go back to X-ray diffraction mode. Now, one feature of this is you don't even need to have a computer to go in the field. This thing will collect everything just from the front panel. And here's everything that this has ever collected. It has a big hard drive on here. And so every pattern that's ever been collected by this instrument is stored. Every single image from every pattern. So everything can be recalculated later on if you find there's a mistake. I can go down here and look at, let's see. There's the opal CT that I showed you in my, there's the opal CT pattern that I showed you. That was taken March 22nd. So all the data is resident in the instrument. So you don't really have to take a computer in the field, but if you want to do analyses in the field, you do. Now I can also run this from my iPhone, which is kind of cool. And so if I go to data, okay, so I'm going to change this to XRF. Oops, I'm on the wrong thing. Well, this is kind of a parlor trick. I really want to show you the real deal. Okay, so here's the XRD pattern. Now, this is a perfectly good pattern to analyze right now. So why don't we do that?
Steve?
So,
Steve?
yes.
This is Hui Feng at Wisconsin. Now we cannot see you. We try all kinds of methods, try to. Well, let's just ask that question. Yeah.
Oh, okay.
Actually, we have a question for you, Dave.
Okay.
How long is it going to take the Mars machine to do this, to load a sample and
Good
unload
question.
it?
Good question. Lot slower than this. Basically, when MSL gets to an outcrop, it's probably going to be 6 days to a week to do a full workup if everything works fine. And it'll go through all the remote sensing, the contact instrument stuff. There'll be, ground in the loop to figure out what to do next. We'll decide to collect a sample or not. That sample is collected by the drill. The new drill is actually a percussion drill. There's no crusher on MSL now, so it drills and crushes a sample. It's sieved, and then that sample is delivered to CheMin and SAM. And that whole process will probably take 4 or 5 or maybe 6 days. And on the last day or two, then SAM or CheMin will do an analysis. We analyze at night because it's colder, and that's what we like to have. We expect that we may take as long as 10 hours to do a single analysis, depending on how complex the material is. For obvious reasons, we wanted to make this thing a lot faster than MSL because you don't want to sit there for 2 days waiting for the results. So this is about, I would say, 25 times faster than MSL is. So yeah, it'll take probably two nights of data, and that'll give us what we're seeing here. The equivalent of about 2 or 3 hours worth.
Dave, is there anything that we've learned about the properties of the soil from Mars Phoenix that leads you to consider any changes or any aspects of the way you're acquiring a sample and getting it in the instrument on MSL?
A lot of that stuff, yeah, good. Yeah, that's a great question. We're really thinking a lot about that now. Well, Doug Ming, who's on my team, is also one of the Phoenix guys. And he's a soil scientist. So
we're puzzling over some of those results. My first answer is let Sam try it first, then we'll do it. And the thing that I'm mostly worried about is some of my other co-Is, Dave Vanneman, Dave Fish, and Steve Chifra, have done a lot of work on iron sulfate hydrates, and these things are real nasty things. Some of these things can when you warm them up, they'll go through a liquid phase, make a slurry, and then lose water and turn into cement. So we certainly don't want that in our funnel when we're trying to collect a sample. So what I would like to do is have a wait and see thing to just watch the properties of the stuff before we do anything. I know, you know, Sam wants to, and so do I, want to see exactly what's there, but I want to be a little cautious in the beginning to make sure we don't pour some cement in our funnel, and that'll be the end of it. Okay, any more questions? Or okay, I'll show you how we analyze this. So you see there's a very nice, pretty nice diffraction pattern developing. So I'm going to go to Files, and I'm going to download one of these patterns. So I'm going to download the K alpha pattern right here. And what I'm doing right now is I'm taking it off the computer on the instrument and bringing it onto the computer that's onto this computer. Okay, and I brought down a format which is compatible with a commercial program which I have on this machine. So here we go. We're opening up this materials data JADE program. There's the very same pattern in JADE. I also have, and not only have the JADE program, which is a search, match, and quantitative analysis program, but also I have the ICDD powder file, which is the powder, a complete powder file of all the minerals that are known. Resident on the machine. So the first thing I would do is go to search match and say I want to look in the minerals files to see what this is and tell it to go. And it asked me a few questions. And well, there you go. It looks like Blake's fireplace. It's calcite. So that was kind of a trivial example, but it'll do the same with complex things. I wanted to give myself something easy so I wouldn't screw it up.
Question.
Yes.
This is John at Ames. It's a great instrument. Have you thought about missions beyond MSL? For example, sending it on some small spacecraft to go and check out some of the near-Earth asteroids?
Absolutely. We're actually working on, yeah, the one thing we have to do is make it smaller. And we actually are building a shoebox size instrument now, and which we're going to take on the Squyres Resolve campaign. And it literally is, it's half the size of this. So we're getting down to something we think can be run on smaller missions. We're shooting for 5 kilograms, about shoebox size, and that includes an automatic sample delivery system so that you pour crushed material in there, it'll sort it into the less than 150 micron material and deliver that to the sample holder. So we have that design, we're building it, and I actually have a couple of proposals in right now to do something like that. But yeah, I'm hopeful we can go to, this is just a general purpose instrument. It's been proposed for a variety of places already. My first proposal was pretty much vaporware. That was when they did the old Champollion for the Rosetta mission. And I proposed this in 1992 with barely more than a napkin drawing. They were lucky they didn't choose me. But yeah, I've been trying a variety of things.
Dave, Geeta from Ames. I had a question. So what enables you to really mine HRI profiles from a 500 kilogram instrument to something that's under 10 kilograms? So what component of the instrument was really helpful here?
Basically, the beginning of it was that, dang, I wish I had brought this, you know, I figured this out when I was a postdoc. And I used to go use this carbon coater over in another building, and there were all these.
Dave, I think repeating the question, I see somebody about raising
question
their
was
hand.
what kinds of technologies were useful or were necessary to make this small? Okay, Yeah, I came up with this idea when I was a postdoc at Ames, and I was rummaging through a bunch of drawers of stuff, and I found this little X-ray camera from the 40s. It's a film camera. It's called a Microfocus camera, and it's about the size of a large orange. And so that was my goal, to make something electronic that would be that size. So the first component we worked on was the camera, and the camera we got down to about this size, not counting the electronics. The real issue was the X-ray tube, and power supplies are just a tough business. And so we now have power supplies that we didn't make. They were made by commercial companies like Oxford Instruments that are about this size, weigh about half a kilogram. So we're getting much better in that regard, and I would say mostly, once we got the geometry, which is a compact geometry, we needed to make the camera small, and then make the X-ray tube small in the power supply. So we're obviously going in the right direction. I'm hoping to get it smaller than 5 kilograms. I don't know if we're going to get there. Certainly a little bit, but not 1, not 2, but maybe 3.
Are there any other questions? Well, if not, let's thank our speaker again. And just as a reminder, the next director seminar will be at the end of September. It will be on September 29th, and it will be Norm Sleep telling us about the habitability of super-Earths. So thanks, everybody, and we'll see you all in the fall, if not before. And thank you, Dave.